Happy to have here this week Yury Makarychev. As probably you all know, Yury has been faculty at TTIC for a while now, working in the approximation algorithm using geometric and other techniques. And my son actually asked me what the talk will be about today. It said shortest path, but then I looked at the abstract. I'm actually curious to see this variation of shortest path I haven't seen before. I'm very much looking to hear about it. Thanks, Yury.
Natya, thank you for the introduction, and everybody thank you for coming to my talk. So today I'm going to talk about shortest path with vector h costs. That's the problem I gave a brief talk last year, but today I want to describe more details and tell you about some exciting recent developments. So my talk will be based on a paper with Max and Erasmo, but I will also mention some results from an ongoing research project with Charlie, Carlson, and Ron. And let me start with talking about the shortest path problem. So shortest path is one of the most basic, widely used and well-studied problems in computer science. The first algorithms for the problem date back to the very early days of computer science. Like Dijkstra's algorithm was developed in 1956, and the Bellman-Ward algorithm was developed shortly after that. However, despite the research on the problem, there are still many exciting open problems, and there are many unexplored research areas in the field. And today I want to talk about one variant of the shortest path problem that hasn't received enough attention. So let me define the LP shortest path. As in the standard version of the problem, we are given a graph G on a set of vertices V with a set of edges E. Also, as in the standard variant of the problem, every edge E has an associated cost CE. However, now costs C are no longer scalars. Instead, they are vectors in some high-dimensional space. So let's say that all costs C lie in L-dimensional space. Importantly, we are going to assume that all cost vectors have positive or non-negative coordinates. As we will see later, if some coordinates are negative, the problems become too difficult. So basically, we cannot do much for it at all. Now, in our problem, we are also given two terminals S and T. Our goal will be to find an ST path as well as a parameter P between 1 and infinity. Now, given any path from S to T, we can define its vector cost. Let's say we have this ST path. Its vector cost is simply the sum of costs of individual edges forming this path. And we want to minimize the LP norm of this cost vector. So we want to find an ST path P for which the LP norm of the cost vector is as small as possible. In other words, we want to minimize this expression, sum over all edges on the path, vector CE, and then we compute the Pth norm. So that's our problem. So today we will mostly talk about this problem. If you have any questions about its statement, it's a good time to ask them.
I think the statement is, to me at least, very clear. But can you maybe say a bit about motivation? I mean, where this?
Yes.
Okay.
So let's start with the basics, and maybe let's first talk about motivation to study the standard shortest path problem. And there are many reasons to do that, but I would say there are two different applications. One of them is to find optimal routes. Suppose that we have 2 points, we want to find an optimal route, and then we solve the shortest path problem. And I guess most of you do that when you get directions from Google Maps or Apple Maps, Waze, and so on. So you ask your phone to find the shortest path from point A to point B. Another slightly different application is as follows. So suppose that we want to perform some task T, and we can do that by making a number of small steps. So initially we are at state S, and we can move from one state to another state following edges of the graph. So let's say from state S, we can get to this state, then we can get to this state, and so on. Our ultimate goal is to get to state T. And we want to do that so as to minimize the total cost of this transition from state S to state T. Now, in our variant of the problem, we assume that there are L different types of resources, and when we transition from a certain state U to another state V, we use all these resources, and our final goal is to find a path that doesn't overuse any of these resources. So we use a small amount of each of these L resources. So that's one reason to study the problem. There is another motivation related to fairness. So we may assume that we have L parties, and moving from state U to state V has different costs for different parties. Now our goal is to find a fair solution, a solution that has small costs for all parties. We don't want just one party to pay for the entire path. And finally, let me mention the original motivation to study this problem. It's related to modeling uncertainty. So assume that there are L possible scenarios, and in each scenario, the cost of edges is different. So in scenario 1, the cost of edge CUV is, let's say, C1. In scenario 2, it's C2, and so on. In scenario L, it's CL. And we want to find an ST path which has a small cost, no matter which of these scenarios takes place. So these are some reasons to study the LP shortest path problem. And let me mention that actually software companies are interested in this problem. And if you want to know more, please ask Max, who knows much more about that. Yeah.
So, okay, I mean, I think I'm completely sold on the multi-objective or having a vector problem. But why LP? Why is LP the right thing or better than L1? L1 here would be very easy, right?
Right.
So why LP?
I mean, let's say if we talk about fairness, then it makes sense to look at something closer to L infinity, right? Exactly, we don't want one party to pay for everything. But in practice, let's say, if we find the route from one point to another, we want to minimize, both like the expected time and variance. And that's closer to L2 minimization. So let's discuss some basic approaches to this problem. And the first idea would be to use to design an algorithm similar to Dijkstra's algorithm or the Bellman-Ford algorithm. So can we use these algorithms to solve the problem? And the answer is no. There are major challenges in adapting these algorithms. And loosely speaking, the reason is as follows. So suppose that we are told that our shortest path from S to T visits some vertex V. And further, we consider two possible ways of getting from S to V, let's say along this path and along this path. Now, if the costs of these paths were just real numbers, we would compare these two costs and choose the cheaper one. That would be easy. But in the vector case, the cost of these paths are vectors, let's say this vector and this vector, and we don't really know which one of them to choose. Yes?
You will probably talk about it, but is it obvious that this program is in polynomial time, even in polynomial time?
It's not in polynomial time.
It's not in polynomial time, but it's a good reason why it's also algorithms free, right?
Right, but potentially you can try maybe design an approximation algorithm based on these ideas.
Approximation.
So in particular, actually, there was a paper that claimed that you should just choose, loosely speaking, the shorter of the path with the shortest, with the vector of smaller norm. But actually, this idea fails completely, and you don't get any non-trivial approximation. That said, we can do something using very basic ideas. First of all, instead of minimizing the LP norm, we can minimize the L1 norm. So let's just replace the LP norm with the L1 norm, and this is equivalent to saying that we just take every vector CE and replace it with a scalar cost equal to the L1 norm of this vector. And then we just run the standard algorithm for the shortest path. If we do that, we get L to the power of 1 minus 1 over P approximation simply because the LP norm and the L1 norm are within this factor of each other. Also, if L is fixed, then Aisi et al. Showed that we can get a 1 plus epsilon approximation. Loosely speaking, we use something like dynamic programming, and we keep track of all possible cost vectors. First, we kind of discretize the space of cost vectors, and then we keep track of all of them. And it's not hard to see that we can get a 1 plus epsilon approximation. We also observed that we can combine the first approach and the second approach, and using completely elementary techniques, we can get a delta times L to the power of 1 minus 1 over P approximation for every constant delta. So these are very basic results. We don't know how to get anything else using elementary.
Do you assume the costs are all positive? Do you assume the cost CE
Yes. All coordinates are positive, yes. So another idea is to use convex optimization. So let's write the following convex program. So of course, in a convex program, we cannot directly optimize over paths. So instead, we say that we want to find a unit flow from S to T such that minimizes this objective, sum over all edges, C, X, E, with if more. You see that in this formulation, all the constraints are linear constraints, but the objective is a convex constraint, so we can solve it exactly in polynomial time. It's easy to see that this is indeed a relaxation. So for every combinatorial solution, for every path P, we can consider the corresponding flow that just goes along this path. This is a valid solution to this relaxation, and obviously its cost is equal to what we want it to be. However, this LP, or this convex program to be precise, has some additional fractional constraints that are not of this form. So now the good news is that the flow polytope is integral. So the set, if you look at the set of all ST flows, they form the flow polytope, and this polytope is integral. So we could hope that we get a good approximation, or maybe even get an exact algorithm, but unfortunately for us, the objective is not linear, and because of that, the optimal solution is not attained at the vertex of this polytope, but rather inside the polytope. And that's a challenge for us. So let's see what the integrality gap of this basic relaxation is. And let's consider the following example. So let's say that our graph G consists of two vertices, S and T. We don't have any other vertices.
When you say all lies inside the polytope, you mean all this lies inside the polytope or may lie inside the polytope?
May lie. I mean, there are some examples where it's integral, but in general.
It can be even in a vertex.
Yes. So let's say that we have two vertices S and T, and they're connected with L edges. And the cost vector for edge number I is simply the ith standard basis vector EI. Now, it's clear that there are exactly L paths between S and T. Each path simply consists of a single edge. And the LP cost of every path is 1 because cost vectors are unit vectors. So the optimal combinatorial solution has cost 1. What about the optimal value of our relaxation? Well, we can consider a solution that sends 1 over L unit of flow along each edge. And the cost vector for this solution is simply 1 over L, 1 over L, and so on, 1 over L. We compute the LP norm of this vector, and we get L to the power of 1 over P minus 1. So we see that the integrality gap is L to the power of 1 minus 1 over P, which is terrible in the sense that we can get this approximation by simply reducing our problem to the standard scalar version of shortest path. So another idea is to take this LP and strengthen it. And this is what Shili, who was a research assistant professor here at TTIC a while ago, and Xu and Zhang did last year. They strengthened this LP by introducing additional constraints, and they showed how to get a log n, log L approximation for p equal to infinity. The algorithm runs in quasi-polynomial time. So that's an amazing result, but unfortunately, this approach cannot be generalized to other values of p, as far as we know, and we tried. They also obtained some other results that I will mention in a second. So let me now tell you what is known about this problem and what we did. So first of all, as I mentioned, there is a simple 1 plus epsilon approximation algorithm for fixed values of L, and there is a trivial approximation of L to the power of 1 minus 1 over P. We can also slightly improve it and get delta times L to the power of 1 minus 1 over P. Now, the first non-trivial algorithm is by Kaspersky and Zelinsky, who showed how to get this big O root n log L over log L approximation for p equal to infinity. They also showed a hardness of log n to the power of 1 minus epsilon for every epsilon greater than 0 when p is equal to infinity. And as I mentioned before, Li et al. Get a log n log L approximation for the L infinity norm in quasi-polynomial time, and they also obtained a big O of d log L approximation for series parallel graphs of depth d, and this algorithm runs in polynomial time.
In the hardness stuff, what's the dependence on L? And this is only when L. I mean, for the hardness result, is this all even with fixed L or only when P is with N?
L will be like N.
Okay.
No results were previously known for P's other than infinity. Let's see, the problem is quite natural when P is equal to 2, but prior to our work, nothing was known for this case. Okay, so let me now tell you what we did. First of all, for every integer P greater than 1, we can get P times log n to the power of 1 minus 1 over P approximation multiplied by delta in quasi-polynomial time and time n to the power of big O of log n. And here constant, this number delta can be made arbitrarily small by increasing the running time. Also, if we can actually save this log n factor by further increasing the running time to something like n to the power of log n to the power of c. This is still quasi-polynomial time, but it's even worse. In an ongoing research project with Charlie and Ron, we proved an almost matching hardness result. So we showed that under kind of standard complexity assumptions, it's impossible to get better than this approximation factor for some constant c. I know that this result is, this number is pretty close to this one. The only difference is that here we have an extra log n factor in the denominator. Yeah.
I'm a bit confused, but how does that agree with the approximation algorithm for p equals infinity? I mean, this would suggest you cannot get any approximation algorithm for p equals infinity.
No, I mean, you should plug in. Okay, this hardness result is for a fixed p. The hardness result is
there exists a p. As in, you cannot get
for integer
p,
p, this hardness result holds. P can also increase, but then kind of the result becomes a little bit different.
Okay.
And for the positive results, we can plug in p equal to log n. In that case, the P norm and the L infinity norm are within a constant of each other. So we can get a result very similar to what Shelley et al. Got, and here we can get a slightly better result by which is better by this log n.
So you should think of p as, I see. So if you want p equals infinity, you really should think of p equals log L.
Yeah. But in this hardness result, p is fixed. We also have something when p is not fixed, but that's not. We also pinpointed the optimal approximation factor for series parallel graphs of fixed depth d. So in such graphs, the optimal approximation factor is given by these d-dimensional Bell numbers. I will talk about them later today. In the most interesting case, when d is greater than log star p, this expression is equal to p times d to the power of 1 minus 1 over p times some constant. So for series parallel graphs, we exactly know what the best approximation is. We also showed log n hardness for p equal to infinity. That slightly improves the previous hardness result of log n to the power of 1 minus epsilon. And we also looked at the problem where costs may be negative, and in that case, the problem is really difficult, so it doesn't admit a better than n to the power of cp over log n approximation. And that, this result is relatively simple. We reduce the problem to the closest vector problem in lattices and get the same hardness. Yes.
Is cost may be negative for p equals 1 even, is this possible?
Even for p equal to 1.
It's hard.
It's hard.
Yeah.
So If p is equal to 1 and all the coordinates are positive, then the problem is equivalent to the one-dimensional problem. But if some coordinates are negative, then the problem is hard. Okay, now let me tell you what we did in our paper, how our algorithm works. First, I want to give a short course on sum of squares. So let's first pretend that we are given a distribution P of ST paths, and then we can consider an HE and introduce an indicator variable XE for this H. XE is equal to 1 if our HE belongs to path P sampled from our distribution, and it is equal to 0 otherwise. So for every H in the graph, we have this indicator 0, 1 random variable. If we have such a distribution of paths, we can define a feasible LP solution XE hat simply by saying that XE hat is equal to the expectation of XE, and this is equal to the probability that HE belongs to our path P sampled from the given distribution. Now we can write expectations of degree 1 polynomials using these newly defined variables XA hat, XB hat. For example, if we have the polynomial 2XA minus XB, then its expectation is equal to 2XA hat minus XB hat. And when we do that, when we derive this expression, we simply use the linearity of expectation. Now our goal is to extend this to higher degree polynomials. How can we do that? We define additional variables for tuples of edges. So let's say we have two edges AB. We introduce this new variable x hat AB, which is the expectation of the product of XA and XB. Since XA and XB are 0, 1 variables, this is equal to the probability that both edges A and B belong to the path. Note that variables XA and XB are generally dependent, so we cannot say that this is simply the product of XA hat and XB hat. That's not true. Once we define these new variables, we can express high degree polynomials. We can express expectations of high degree polynomials. For example, the expectation of XA plus XB plus 2XA times XB is equal to this expression. Okay, but in reality, we are not given any distribution of paths, but let's assume that we have we still have values of x hat variables. So we know what XE hat, what XAB hat is, and so on. Then we can pretend that there exists some unknown distribution P for which these XE hat, XAB hat, and so on are the desired marginals. In other words, the expectation of XE is equal to XE hat, the expectation of XAB is equal to XAB hat, and so on. And in this case, we can still write what the expectations of these variables, these polynomials are. Note that in order to do that, we don't really need the full description of our distribution. It is sufficient to know just what the values of these x hat variables are. And moreover, if we have these numbers x A hat, XB hat, and so on, but there is actually no distribution consistent with them, we can still use the same formulas and define the expectations of various polynomials. But of course, in this case, this will no longer be a real expectation. This will be a pseudo expectation. So we will say that the pseudo expectation of xe is this xe hat. The pseudo expectation of 2xa minus xb is 2xa hat minus xb hat, and so on. Yes.
I'm sorry if I missed it, but are we now assuming that p is equal to 2 or not?
No.
Okay.
But we consider, in this example, I just wrote tuples of size 2, but in general, we consider larger tuples as well.
Oh,
so we also have
So
variables
you're not
x
claiming,
hat,
right?
AD,
Yes,
CG, and so on.
Are you taking unit? Are you taking p to be integer?
P is integer.
Okay.
That's why it came in that result.
P is integer. So our goal now is to write a convex program involving all these new variables, like the original ones plus new ones, add some consistency constraints that make sure that, let's see, the value of xab and the values of xa and xb are consistent in some way. We also add some SDB constraints, and we solve and find these x hat variables, and they define a pseudo expectation. So there is kind of a standard way to do that. I'm not going to describe it, but the key point here is that we can find an optimal pseudo expectation of degree d in time n to the power of big O of d. And this pseudo expectation will satisfy many, but not all properties of a real expectation. Let me just mention some kind of basic properties that a pseudo expectation satisfies. For example, as a standard expectation, the pseudo expectation of a constant is equal to the constant. Let's say the pseudo expectation of 1 is 1. Then pseudo expectation is a linear function. That's a very important property. So the pseudo expectation of alpha f plus beta g is just, alpha times the pseudo expectation of f plus beta times the pseudo expectation of g. Now, another key property is that the pseudo expectation of a sum of squares is greater than or equal to 0. So for any polynomials f1, etc., fk, the pseudo expectation of the sum is greater than or equal to 0. And because of this property, this relaxation, this type of relaxations is called sum of squares. And finally, we will require that the pseudo expectation of xe squared is equal to the expectation of xc. This is a valid constraint because xe are supposed to be indicator 0, 1 variables, and if xe takes only values 0 and 1, then of course this is true. So let me now write our SOS, like sum of squares relaxation. Now the objective is the pth degree of the LP norm. So we take the sum over all edges on the graph, CXC, so that was our previous objective, but now we raise it to the power of p. We get a degree p polynomial, but as we discussed, in an SOS relaxation, we can have higher degree polynomials, not only linear polynomials. And we use the same constraints as before. We still require that X defines a unit ST flow. For convenience, let's introduce these extra variables XU. So XU is the amount of flow that enters vertex U. And it is equal, this first constraint tells us that XU is equal to the amount of flow that leaves U. And the second constraint tells us that XU is equal to the amount of flow that enters U. This constraint XS is equal to 1 simply says that the amount of flow is equal to 1. Any questions about the relaxation or about the sum of squares? Yury?
So I'm not sure if to ask this now or later, but I mean the runtime here, you give a runtime dependence on P, then also like an exponential runtime. So is that really in your methods? Is that the case, or are you going to fix that?
We get quasi-polynomial time because of that. So our algorithm is a quasi-polynomial time algorithm.
You don't.
No, not only because of that, but that's one reason why.
So that really your final algorithm you will in fact have.
Yeah.
So you have basically a exponential in exponential in log L or something like that.
Yes. Okay. Yeah, it will be exponential in L, but also.
In L, not in log L.
So it will be exponential in P. Not
in P,
in L,
but
but
P. Okay, I'm thinking of P, but P is bounded by log L essentially.
Yeah.
You don't use here any kind of Shirley-Adams constraints.
I mean, we use like the SOS hierarchy, and it includes all Shirley-Adams constraints.
Oh, it does, yeah?
Yeah.
Okay.
Okay. And now let's discuss an algorithm for series parallel graphs. And there are several reasons why we focus on series parallel graphs. I'm going to define these graphs in a minute. First of all, our algorithm with series parallel graphs is much simpler, so it will be much easier to describe and analyze it. Then, for series parallel graphs, we know exactly what the best approximation factor is. It's given by these t-dimensional Dal numbers. And finally, there is a black box reduction from arbitrary graphs to series parallel graphs. So if we just plug in d equal to log n, then we will get an algorithm for arbitrary graphs. That's kind of, this reduction is not the best way to get an algorithm for arbitrary graphs, but this is a possible way, which gives an algorithm with a slightly suboptimal running time. Okay, so now let's define series parallel graphs. And we start with series parallel graphs of depth 0. So a series parallel graph of depth 0 consists of two vertices, S and T, connected with several parallel edges. Now, a depth 1 graph is obtained by serial composition of series parallel graphs of depth 0. So we take one, we take we take several graphs of depth 0 and then just combine one after another. We can also take several graphs of depth 1 and combine them in this parallel way, and we still get a graph of depth 1. Then we combine graphs of depth 1 in a serial way, and we get a series parallel graph of depth 2, and so on. In general, if we have defined a series parallel graph of depth I, we get a graph of depth I plus 1 by taking series parallel graphs of depth I, combine them in this series way, and then combining obtain graphs in a parallel way. So that's the definition. Okay, now let me just describe the algorithm. And the algorithm is surprisingly simple. So we start at vertex S. We look at all edges leaving S. Our SOS relaxation gives probabilities for these edges. The probability of choosing edge E is simply the pseudo expectation of XP. The fact that we have a unit flow tells us that the sum of all P's is equal to 1, and therefore we can sample one of these edges with probability P. We do that, choose one edge, let's say we choose edge SV here, and move to vertex V. And then we want to repeat the same process over and over. There is a slight twist here that if you look at all edges leaving V, then now the sum of the sum of their probabilities doesn't add up to 1, but we choose probabilities proportionally to the pseudo expectations of these edges. So in this example, we see that the pseudo expectation of one edge is 0.2, the other one is 0.3, and the third one is 0.3. So we choose probabilities proportionally to these numbers. And we repeat this step over and over until we reach vertex T. So that's simply a random walk. Now let's analyze what approximation we get using this approach. And let's define cost polynomials. So first of all, for every HE, we define polynomials FEI. FEI is equal to the cost of the ith coordinate of cost vector for HE multiplied by XE. We pay this cost if X is equal to 1, so we use this H, and we don't pay it if XE is equal to 0. More generally, if we have some block in our series parallel decomposition, we define the cost polynomial for this block, FBI. It's equal to the sum over all edges in the block, FEI. So intuitively, FBI is the SOS cost of block B, and we can also look at the actual expectation of FBI with respect to the distribution of paths that our algorithm produces, and that will be the kind of So we can consider the expectation of today we will also consider the expectation of FBI with respect to kind of the actual expectation that our algorithm produces. Now, what is the SOS objective? The SOS objective is equal to the sum over all edges, CXE to the power of P. It's written over there. And it's easy to see that it can be written in terms of these newly defined cost polynomials. So that's simply the sum over all coordinates I, FGI to the power of P. So in the definition of FGI, we go over all edges in G and add up their cost polynomials. Now, what is the actual cost of the path that our algorithm finds? Well, the cost of the power of P, the expectation of the cost of the power of P is given by this expectation. So here again, we can use the same polynomials. Now, it's easy to prove that the following equalities hold. So let's look at the expectation of XE. In other words, in the probability that our path P visits HE, and at the pseudo expectation of XE. And it's not hard. It's not hard to prove by induction that these two are equal. And also, we can look at the probability that our path visits vertex U, and again, by induction, we can prove that this is equal to the pseudo expectation of XU. So at least we see that there is some connection between expectations and pseudo expectations. So this is good news for us. Now, to prove, suppose that we want to get an alpha approximation, then we need to prove that the expectation of fgi to the power of p is at most alpha to the power of p times the pseudo expectation of the same polynomial. By the linearity of expectation, it is sufficient to prove that this inequality holds separately for each coordinate I. So once we prove that this holds for every coordinate I, we simply add these inequalities over all i's and get the desired inequality. And this means that basically we need to analyze a one-dimensional problem where all costs are one-dimensional. And because of that, to simplify the notation, let's just pretend that our costs are one-dimensional, and we will not write I again to simplify the notation. So now our goal is to prove this inequality at the top of the slide. And let's see what fg to the power of p is. Well, fg is equal to the sum over all edges e, f, e. We raise that to the power of p, and we get the sum over all possible choices of e1, etc., ep, fe1 times fe2, and so on, fep. Now, to prove the inequality at the top of the screen, it would be sufficient to prove this, a similar inequality term by term. So it would be sufficient to prove that the expectation of this product is at most alpha to the power of p, the pseudo expectation of this product. But unfortunately, this is not true. This is not true for any alpha, and the reason for that is that it's possible that this pseudo expectation is equal to 0, but that expectation is strictly positive. So an approach like that wouldn't work. Now, let's try to do something differently. And as a warm-up, let's consider the case when p is equal to 2 and d is equal to 1. So our series parallel graph is very simple. It looks like this, and p is equal to 2, so we are considering products of the form fe1, fe2. So let's write what the expected cost squared is. It's equal to the sum of over e1 and e2, fe1, fe2. And now we split the sum into two sums. In the first sum, we consider edges e1 and e2 that belong to the same block, like is shown here. So e1 and e2 belong to the same block. And in the second sum, we consider e1 and e2 that belong to different blocks, b1 and b2. And we are going to analyze these expectations separately. So first, let's assume that e1 and e2 are in the same block. And then there are two possibilities. The first one is that e1 and e2 are distant edges. And in this case, the probability that our path visits both of them is 0. So here we are talking about an actual path that we find, and of course, this path cannot visit both edges, like this edge and this edge. It may visit only one of them. In the second case, e1 is equal to e2. Let's say it's equal to e. And in that case, we write that the expectation of fe1 times fe2 is equal to the expectation of fe squared. Now we write the definition of fe. Fe is equal to ce xe. And we know that xe squared is equal to xe. And therefore, the expectation of fe squared is equal to this expectation. Recall that that I mentioned that the expectation of xe is equal to the pseudo expectation of xe, and therefore here we have that this expectation is equal to this pseudo expectation, And again, this pseudo expectation is equal to the pseudo expectation of Fe. So we are in good shape. Now we consider the sum of all E1 and E2 that belong to the same block using we know that from the previous discussion, we know that this is equal to the pseudo expectation of the sum over all edges, Fe squared. Now, this is upper bounded by this sum. That's easy to see because in the expansion of this sum, we have, in particular, these terms, and we have some other terms as well, but they are non-negative. And this expression in the parentheses is simply Fg. So we get that the expectation of this first expectation is upper bounded by the pseudo expectation of Fg squared. So now let's look at the second case, and in the second case, E1 and E2 belong to different blocks. Note that our algorithm chooses edges in B1 and B2 independently, and because of that, the expectation of Fe1 times Fe2 is simply the product of expectations, and now we can use that each of these expectations is equal to the corresponding pseudo expectation. So now we consider this the expectation of the sum of Fe1, Fe2. Here we assume that E1 and E2 are in different blocks. We move to pseudo expectations, and we get that this is upper bounded by the expectation of Fg squared. So we are almost done. We have this upper bound, but we want to get this upper bound. That's the SOS objective. Note that if we had real expectations, then this inequality would be trivial because the difference between the right-hand side and the left-hand side is nothing else than the variance of Fg, which is always non-negative. But it turns out that this is also true for pseudo expectations, and we use this fact. And so combine what we got, we get an upper bound. The expectation of Fg squared is at most 2 times the pseudo expectation, and that means that we get a root 2 approximation algorithm. Now, let me tell you what we do in general, and when d is equal to 1, we consider the expectation of the product of the form F, E1, etc., F, EP, and our previous discussion suggests that we should kind of figure out which of these EIs and EJs are equal and which are not of them are not. So we consider the partition of edges EI into those that are equal and those that are not. And it turns out that for every partition, we can prove that the expectation of this sum is upper bounded by the SOS objective. So at the end of the day, we get that the sum over all possible choices of E1, etc., EP is upper bounded by the number of different partitions of a set on P elements. So we get this upper bound on the approximation ratio. When d is greater than 1, we use basically the same idea, but it becomes a little bit more complicated, and we need some additional inequalities for SOS pseudo expectations. So let me finish here, and tell you about some other results that we got. So using these techniques, we also got an algorithm for the Group Steiner Tree problem for group asymmetric TSP. And the main open problems in this area are to design a true polynomial time algorithm for shortest path. So far, basically, we don't know any polylogarithmic true polynomial time algorithms for the problem, and also to design an algorithm for non-integer values of p.
Questions? So if I followed correctly, then in some sense the series parallel analysis just gives you generic statements about the pseudo expectation relaxation. Is that something that's more broad than? Is this correct? Is this something that is more broad than just the specific shortest vector problem that gives you?
I mean, these are like in some sense they're specific to our problem. So we consider we consider two types of compositions.
So you have another problem that I want to look at the path parallel and path polytope and use a sort of the same relaxation, a sort of probability relaxation to it. Would I also kind of automatically get the same benefits if the graph is series parallel?
Once again, if you
I have a different problem on the path polytope that uses the can I kind of use this as a generic way of approximating the path polytope and get the same benefits from series parallel without even thinking about the fact that without doing anything special to think about my series parallel in the context of my specific problem?
If you have additional constraints, let's say on this path, then yes. So if you want to, right. So if your objective is to minimize the LP norm, but you impose some additional constraints on the path, then you can still use this algorithm and you will get the same approximation guarantee. That's true.
But if my objective is any other degree p constraint, to degree p objective. Or anything else I could express with the pseudo likelihood for order up to p. Okay, maybe
it's not clear. I mean, it should be defined more formally.
Other questions?
So if the h weight vector, like for each coordinate, is bounded in some range, for example, the upper bound is at most some constant times the lower bound is more easier, because I think the LP integrated gap instance would not hold.
I mean, yeah, I don't know. If they within a constant factor, then the problem becomes very easy. You can get a constant approximation.
Okay.
But otherwise, yeah, I'm not sure.
So that's the question. I'm curious. When you said this is used a lot of industry, is it used for very large L or for small L's?
Should ask the max.
Should I ask who?
Max. Max FM.
Yeah,
What's the question?
When Yury mentioned this is used in a lot of industry, I'm curious if it's used for very large L, because these type of approximations would be relevant for large
Yes.
L,
I
or for
feel
like L equals 5.
like moderate, like basically, yeah, it's some L equals 5 is like closer to the industry applications.
But then
It's like some number of multiple objectives that you're trying
Right.
to optimize over.
But it's like not the number. I mean, each objective is actually a specific thing.
It's like
not
a
that I have-
resource or some kind
Yeah,
of
it's not like parameters that I have like a bazillion of them.
yeah.
But in that case, just the trivial approximation is probably in some sense better than.
I mean, in industry, you do care about getting like as good a solution as
No,
possible.
that's true, but would this be actually, would approximation guarantees here be better than just saying that the L1 norm is approximation to LP to any LP norm in R5?
Yeah, that's a good point. I would say so for this specific this is like a very particular instantiation of the general problem of shortest path of multiple objectives, right? And here it turns out to be quite hard. There's other ways of looking at the problem where, like for example, you take some linear combination of the objectives. Like maybe one way to think about this is I give you some oracle where you give me some linear combination of the objectives that you want me to optimize over, and I will give you some solution that's good for that, right? And I should be able to do that without kind of like recreating the graph each time or something. Yeah, so I would say like this, maybe this particular way of phrasing the problem is a little bit too hard for industry applications, but in general, this like multi-criteria optimization is useful.
Okay, other questions or answers from the audience?
It sounds like very reasonable to have a distribution, to allow distribution of parsing of the single path if your motivation is to be fair, right? So this also makes problem simpler.
This is also interesting. Yeah, I guess. Yeah.
Because
I'm
now
happy
the
about
expected cost then is lower for everyone.
I agree. Yeah, it's also interesting.
Okay, let's thank Yury again. And